Welcome to UGC lecture series Linear Integrated Circuits. So, in this lecture we are going to discuss about the operational amplifier basics, op-amp modes, op-amp parameters, negative feedback circuits, inverting and non-inverting amplifiers and voltage follower. The operational amplifier is otherwise known in short it is called as op-amp. This is the symbol of the operational amplifier, or you can say it is op-amp. There are two input terminals, positive and negative input terminal. Plus is a positive input terminal. Here you can give a signal, say it is V1, and negative terminal minus symbol represents the negative terminal, to which you can give another signal, say V2. You have to give two power supplies, VCC and minus VCC. The output can be taken here. And this diagram is giving you the pin detail of IC 741 or operational amplifier. Operational amplifier which has 8 pins here. The first pin and the fifth pin which shows offset null. This is for making the output voltage 0 for the input voltage 0. So, if sometimes the output voltage will be some volts in the range of milli or nano volts, even though the input voltage is 0. In that case, you have to use these pins 1 and 5 to give some input voltage to make the output voltage 0 for the signals 0. The supply, these are the supplies and these are the signals. The supply is different from the signal. Supply is given for the IC to work, and signals are given for to the operational amplifier in order to process the signals. If the signal needs to be amplified, then the signal is given here as V1 or V2, but in that case also for this IC to work you have to give the supply. So, supply is different from the signal, and in what I have discussed is offset null pin 5 and 1, which is given with some input voltages in order to make the output voltage 0 for 0 signal. If there is no signal, sometimes the output will be present in the range of milli or nano volts. In that case, to make this output voltage 0 for the input voltage 0, we are giving some voltage to the first and fifth pin. And second pin is the inverting input terminal. Here it is second pin, and third pin is the non-inverting input terminal. Fourth, you have to give the negative supply voltage, and sixth is you can take the output from the sixth pin. Seventh pin the positive supply voltage, and eighth pin has no connection. These are the pin details of this IC 741 here, which is given as 741, which is the product of Fairchild manufacturer of IC. This circuit diagram shows you the connection of the power supply. So, we know that the fourth pin and the seventh pin is used for the power supply. Here this seventh pin has the positive terminal of one of the power supplies connected to the seventh pin, and whose negative pin must be grounded. The negative terminal of this particular power supply must be grounded, and here the fourth pin has negative supply. If you see the pin detail, the fourth pin of 741 has negative supply. Here the negative terminal of the power supply is connected to the fourth terminal, and whose positive terminal must be grounded. So, sometimes in the laboratory, if you connect this supply voltage, some will connect the positive terminal to the seventh pin and negative terminal of the same power supply to the fourth pin. So, you have to make sure that those connection is not correct. So, you have to use two RPS or two power supplies, where one of the power supply must be given to the seventh pin and the other power supply must be given to the fourth pin. So, this we have to ensure before doing any application of 741. And this is the 741 IC, which is the Fairchild semiconductor product. This IC 741, or you can say this is a mu A 741, is the manufacturer name is Fairchild Semiconductor for mu A 741. Similar 741 series can be manufactured by other manufacturers like Signetics and so. So, this operational amplifier, why it is called as operational amplifier, or in short it is op-amp, because using this device, using this active circuit element, all the mathematical operations such as addition, subtraction, division, differentiation, integration, log, anti-log, all these operations can be made possible. So, it is called as operational amplifier. This is the internal circuit of the operational amplifier. We know that it has two input terminals, inverting input terminal and non-inverting input terminal. Here this is given here, represented here. To the base of Q1 is the non-inverting input terminal and base of Q2 has the inverting input terminal, and this is connected as a differential amplifier. And here you can notice the positive supply and the negative supply. This VCC is the positive supply given, and this minus VEE is given for the negative supply, and the output you can take it in between the resistor R6 and R7. So, this circuit is, this operational amplifier IC741 is made up of n number of BJTs, or you can, or this IC741 is also made by using the field effect transistors. And this circuit shows the ideal operational amplifier circuit. Here these are the two input terminals for which we have given the voltages V1 and V2, and across these terminals you can calculate what is the difference between the input voltage, and internally it has a input resistor, it is designated as Zn, and here this is the voltage source A V2 minus V1, this is voltage gain, and the output resistor Z out is connected in series, and from which you can take the output of the operational amplifier, and here the supply voltage, positive and negative supply voltage is given. This is the ideal operational amplifier circuit. The ideal characteristics of the operational amplifier is the input impedance must be equal to infinity. Why? Because even a lower amplitude signal can be used, can be amplified by using an operational amplifier. If this input impedance is very high, then this resistance will not act as a load to the lower amplitude small signal at the input terminals. So, this input resistance must be very high or infinity ideally. The output resistance is 0. In this case, Z out must be equal to 0 ideally, since because the voltage, the amplified version of the input voltage can be taken as such at the output of V out when this Z out will be 0. If this is 0, then you can treat this as a short circuit. So, the output will be exactly equal to the amplified version of the input signal, and bandwidth is infinity. Why? Because almost all the frequency signals can be passed through this the operational amplifier. So, it should have a infinity bandwidth or a higher bandwidth practically. Open loop voltage gain is infinity. Here this gain must be, the open loop voltage gain must be infinity in order to get the maximum amplification factor or a maximum voltage at the output for even for a lower input signals. Then the offset voltage is 0. Just now we have discussed about the offset voltage. This is actually the voltage present at the output if the input voltage is 0, if the input signal is 0. So, if it is 0, then the output voltage must also be 0. So, ideally the offset voltage is 0. So, these are the ideal characteristics of operational amplifier, to which there are another two parameters called CMRR and slew rate. The CMRR is the common mode rejection ratio, which has to be infinity, and slew rate, which is which has to be also infinity. We will see it in the next slides. So, this is the operational amplifier ended input. Then what is the common mode rejection ratio, CMRR? It is defined as the measure of an amplifier's ability to reject the common mode signal is called CMRR. To reject the common mode signal, in the sense it has to reject the noise. So, it is the common mode rejection ratio. So, the gain should be very high for the desired signal, or you can say it is a different signal, and 0 gain for the common mode signal. So, it is the common mode rejection ratio is the ratio between of the difference mode signal to the common mode signal. The CMRR in dB, it is calculated as 20 log AD by AC. Ideally, the CMRR is infinity because we know that the common mode signal must be equal to 0. The operational amplifier has to reject this common mode signal. So, the gain must be 0. So, the CMRR must be infinity ideally. We will be seeing about two configurations of operational amplifier. One is open loop configuration, the other one is the closed loop configuration. In the open loop configuration, when you look at the circuit here, there is no loop present in between the output to the input. You have two input terminals, you have given the input values, input to the two input terminals, and you are taking the output, that is all. So, here this open loop configuration of operational amplifier will work as a switch, or you can say the output will get transited in between two values, just two values. The values are plus or minus V saturation. And what is the saturation value? We have just now seen the transfer function of the ideal operational amplifier. The saturation value is, it is 1.3 or 4 volts lesser than the supply voltage which we are giving to the 7th and the 4th pin. So, if the voltage present at the second terminal is high, say this is the negative terminal, if this is higher than the signal present at the positive terminal, the output will be a negative V saturation. Just the output is getting transited between two saturation values. So, if the second pin has the highest value than the third pin, and since this is the negative terminal, it has a 180-degree phase shift. So, it has the minus V saturation. And for the next case, if the third pin has a higher value than the second pin, then it has a positive V saturation. So, the output is either positive V saturation or negative V saturation. So, you can say this action as a switch. So, open loop configuration of operational amplifier will act as a switch, or you can say it is a comparator. Okay. So, here this waveform is given as one of the input signal, and this reference is given as the other input of this operational amplifier. So, whenever the waveform, the AC current or AC voltage is just exceeding this V reference, then you have a transition at the output. This is the operation of a comparator here. So, here the voltages are compared at the two inputs, and based upon the magnitude of the input voltage, the output will get the transition in between the plus or minus V saturation, which is actually the supply voltage. This is an example of a closed loop configuration of operational amplifier. Here also we are giving two input signals, say V1 and V2, and the voltage at the output is fed back to the negative terminal through the resistor. So, this is said to be a closed loop configuration. So, in the closed loop configuration, we have to assume that the gain is very high. So, the voltage difference between these two terminals is 0, the gain is infinity, and the resistance at the input side of op amp is infinity. So, the current drawn by the two terminals plus and minus is equal to 0. So, with these assumptions, we have to find out what is the output of any closed loop configuration. So, this is one example of closed loop configuration, and this circuit is called as a differential amplifier circuit, since we have given two input signals at the negative and positive terminals. Since we have a negative feedback, because the feedback, the output is given to the negative terminal, and so it is a negative feedback. Once the negative feedback is given, then the operational amplifier will work as an amplifier. If a positive feedback is given, then it will work as an oscillator. So, here this is the differential amplifier. The output will be the amplified version of the difference between these two input signals. If these two input signals are 0, then the output must be 0, because the mode of operation is common, a dual input mode, but a common mode signal. Since these two signals are different, V1 and V2, then the difference between these two signals will be getting amplified at the output. So, here this is the output of the differential amplifier circuit. V out is equal to plus or minus ACL into V1 minus V2. Here, why this plus or minus? Because the difference between the two input signals may be either a positive value or a negative value. So, you can always have a plus or minus, and which is the gain of the closed loop circuit ACL. So, it is the difference is getting multiplied with the gain, and it may have a positive value or a negative value. That is the output of the differential amplifier, and the feedback is said to be positive if part of the signal from the output terminal is given back to the non-inverting terminal of the operational amplifier. Here we have given to the inverting amplifier, but this feedback is said to be a negative feedback. If it is a positive feedback, you have to give the output to the positive terminal. In that case, the circuit is an oscillator. The positive feedback is used in on oscillators. If the feedback is negative, then it is an amplifier circuits. So, this is two amplifier circuits we can have using the operational amplifier, and as I said, there are two important rules for analyzing the circuit. One is no current flows into the input terminal since the input resistance is infinity, and the next one is the difference input voltage is 0 as V1 and V2 is equal to 0, virtually equal actually. And can you guess what is the circuit for this inverting amplifier? Just now I have told you about the feedback type of the feedback for a amplifier, and since it the name itself says it is an inverting amplifier, you have to give the signal to the inverting terminal and the feedback to the negative terminal. Say this is R1, the signal is given to the inverting terminal, and since it is an amplifier, the feedback is given to the negative terminal through the resistor RF, I can say, and the positive terminal is simply grounded. So, this is the circuit of an inverting amplifier. Consider the current flowing through the resistance as I1, the same current will flow through the resistance RF. Why? Because this current is equal to 0. So, we have assumed no current flows into the input terminal since the input resistance is infinity. So, now I am going to derive the equation for the gain of the amplifier, inverting amplifier, as minus RF by R1, for which I1 is given as Vi by R1, and the output voltage V0 is given as this voltage. The output voltage V0 is given as minus I1 RF, since we are taking from this point to the ground terminal, but the current is flowing towards this point. So, you have to take the feedback current as the reverse of this input current. So, substitute I1 here, it is minus Vi by R1 into RF, and from this equation if you take V0 by Vi, then it is minus RF by R1. So, this is the gain of the inverting amplifier circuit. A question is, design an amplifier for the gain minus 10 or minus 5. The design an amplifier with the gain of minus 10. Then you have to design an amplifier which should be a inverting amplifier. So, A is equal to inverting amplifier's gain is minus. So, minus RF by R1 is minus 10. Why this minus is? This is the we have given the input signal to the negative terminal. There will be a 180 degree phase shift between the input and the output voltages. Okay, here assume the value of R1 as 10 kilo ohms, then find out RF from this equation. So, here from this equation it is 10 into R1. So, here 10 into 10k. So, the RF value is 100k. So, this is the gain of this is the resistor's value. R1 you are assuming as 10 kilo ohms always, because it has to be high. The input resistance must always be high, since it should not act as a load to the small signals, and from this you have to calculate what is the value of the feedback resistor. And the next circuit is a non-inverting amplifier circuit. You can easily draw this non-inverting amplifier circuit. Since it is an amplifier, you have to give the feedback to the negative terminal through a resistor RF. So, I am giving a feedback to the negative terminal through the resistor RF, and this is R1, here it is grounded. And since it is a non-inverting amplifier, I am giving the signal to the positive terminal. So, here output is taken. This output must be equal to 1 plus RF by R1 into the input signal. We have considered two common rules, say no current flows into the input terminals, and the difference between the input voltage V1 V2 must be equal to 0. So, you have to consider that this node and this node are virtually equal, because the difference between these two voltages must be equal to 0 in order to get the high gain or infinite gain. So, I am taking this node voltage as Vi. Whatever the voltage at this node is taken at the voltage here. So, Vi is present here virtually. So, I am calculating what is Vi. So, from the output voltage through the potential dividers RF and R1, I am calculating what is Vi, V0 into the resistor R1, across which I am calculating Vi, divided by the total resistance R1 RF. So, from which I can easily write V0 by Vi as R1 plus RF by R1, from which 1 plus RF by R1. This is the gain of the non-inverting amplifier circuit. So, here there is no phase shift between the input and the output, as in the case of the inverting amplifier. It is a non-inverting amplifier, so there is no phase. And also one more point you have to note down: since this signal is directly given to the positive terminal, there is no resistance here, as in the case of the inverting amplifier, where in the inverting amplifier we have given signal to this resistor and we have made this positive terminal grounded. So, for that circuit the input resistance is R1, which we are assuming it as 10 kilo ohms. But here in the non-inverting amplifier there is a significance that this voltage is facing a high input resistance, and which is nothing but the internal resistance, because we have connected it directly to the positive terminal. This signal, even a small signal, can be amplified by a non-inverting amplifier, since its input impedance is very high when you compare it with the inverting amplifier. And from this circuit we can construct one more circuit called a voltage follower circuit. So, what is a voltage follower circuit? Here in the voltage follower circuit, the output will be equal to the input. For the voltage follower, from the name itself we can understand that the output voltage is the input voltage, or the output follows the input. So, we know that the gain of the inverting amplifier is 1 plus RF by R1. This is the gain of the inverting amplifier. This is the feedback resistor, this is the input resistor. And this gain is given as V0 by Vi. This is the value of the non-inverting amplifier. If you want to have V0 is equal to Vi, this is the voltage follower circuit. If the output voltage follows the input voltage, then that is the voltage follower circuit, for which what you have to have is this RF must be equal to 0, and this R1 need not to connect, or you can say this R1 must be equal to infinity. So, in the circuit If RF is 0, then it is a short circuit. If R1 is infinity, it is a open circuit. So, in the non-inverting amplifier, if you have a short circuit instead of an RF, here you have RF, but if it is shorted, then also if input resistor is open, this is R1, it is open, and here you can give any input signal, say Vi, then your output voltage will be equal to the input voltage. If this if the values of RF and R1 is 0 and infinity respectively, then the output voltage will be V0 is equal to Vi. This is the voltage follower circuit from the non-inverting amplifier circuit by having the values of RF and R1 as 0 and infinity. And this circuit is also having a high input resistance, and so always we can use this circuit as a buffer circuit in order to prevent the loading effect. So, in this lecture we have seen the operational amplifier basics, the negative feedback concept, and inverting and non-inverting amplifiers, and finally the voltage follower circuit. Try to answer this. Why an operational amplifier is called as op amp? List the ideal characteristics of op amp and define the CMRR.